Okay, very good. Welcome again. So we will continue our discussion of the Maxwell's equations, which is chapter 2, and then we will jump to electrostatics, hopefully today. For this chapter and no, this chapter especially, there's going to be a lot of reading for some of the philosophical ideas and differences between microscopic, macroscopic, and some of the heuristic arguments you can actually make to arrive at Maxwell's equations using just simple physical arguments and dimensional analysis as opposed to the actual rigorous mathematical derivations. Okay, so let's hope this works. So I'm trying something different today. Okay, it's getting there. And okay, so let's get started. We were discussing how the different kinds of charge distributions can be used to determine the charge density, or rather the total charge if you have a line charge density or a volume charge density or a surface charge density. Each one of those have slightly different expression. Let's now take a look at the discrete case. And in the discrete case, you can still use the definition of the charge density volume, the total charge in terms of the volume charge density. This is still okay to use, but what you have to realize now that the charge density is now discrete, and so the discreteness would come through the finite summation of the charges that you have, and it's going to, let's say the index is k equal to 1 to n. Let's say you have n discrete set of charges at positions rk, and the amount of charge situated at that position is qk. Then you can use the Dirac delta function to pick out the position. So there's a filter property of the delta function can be used actually to pick out the positions. This filter function goes in here, and then even though the charge density may seem like a continuous function there, because of these deltas, it will pick out the discrete positions, and you will get the charge density. Okay, so this is a very important trick.
Kapale,
Yes.
as it is discrete, why don't we use Kronecker delta?
Because the argument is still continuous, right? So because R is continuous, you cannot use Kronecker delta really. These are not discrete indices. These are, you still have the continuous space, and at specific positions in this continuous space, the charges are situated. So there is no way of using Kronecker delta to describe this. You have to have, this delta function, which takes over the whole space, but it is zero everywhere except at the positions of the charges. So this is still a continuous function. That's what the Dirac delta function sort of allows you to do. It allows you to take into account discontinuities or specific positions within the 3D space that are of interest. So you can pick those out because of this filter property, right? So this is essentially a filter function. Okay, and you continue to think about it a little bit, and if you have any questions, specific questions, or if you tried to express this in terms of delta ij, the Kronecker delta, we would like to hear from you. Okay, so you could try that, Ashukur. So let's now take a look at the current. So later on, We will take a look at a couple of examples of this after we are done with some of the today's topical discussion. So remind me of that if I forget, right? So we want to look at more examples. Okay, let me highlight that. Okay, I will come back to it later. Let's now look at the current distributions. And there are, of course, variety of different distributions that we are going to get. Even though the important thing to remember here is, even though we are looking at statics, electrostatics and magnetostatics, what we mean there is that the charge rho is essentially just a function of position and no time dependent. Okay, but that does not preclude us from having currents. We can have a continuous flow of the charges through certain current carrying conductors or surfaces, and that would still allow us to stay within the static domain, right? So this is the standard definition of the current.
Dr. Kapale,
Yes.
I think you have to little bit reduce the zoom.
You cannot see it.
Yeah, for the corner, yeah, we can see.
Okay. Let me see what's happening. How about now?
It's good now.
Okay, well, I'm going to actually try to do it this way. Is this better?
Yeah, this one is better.
I didn't do anything yet. Sorry. Give me just a second. I'm going to have to do that slightly less so that I can see what I'm going to try to. I need to look at my notes, so I cannot have this thing occupy the whole screen. And so that's kind of what's happening now. How about now? Are you able to see it fully, the whole page?
Yeah.
Okay. All right, so let's do it this way. So now you know this is the standard definition of the current that you get from your undergraduate classes. What we are going to do now is add a bit more complications to it or sophistications to it, where here now we are assuming that you have some surface over which the current is flowing. And at each point in space, you have some current density J. And J in principle, again, could be the function of position and time, but we are going to assume time independence. And so then you would have steady currents, which are not changing, right? And J actually comes from, if you want to think of a charge density that's moving at certain speed, then you can look at J as rho multiplied by V. And J itself, you remember, is a vector quantity. And that's why you always need here ds dotted with J. So this is no volume integral. For currents, you always need sort of surface integral to calculate the current passing through a certain region of space. For the surface currents, so J, the units are still Coulomb per second per meter cubed, right? Because it's still a density. Let's see, would it be meter cubed? No, it would not be. It would be just meter squared. Why? Because you can look at this here. That's Coulomb per meter cubed for the charge density multiplied by meters per second. And that gives you the unit for the current density. Now you can have surface currents like I showed you here in the diagram, where You have a surface charge density moving in a certain, with a velocity vector v. And in that case, so you have a surface charge that's moving. In that case, the current is defined through a line integral, dl, along a certain contour or a loop that you choose over this surface. So let's draw a little picture here. And you are looking at a small line element dl, and that's your contour on which you are moving along. Then again, you need to figure out the current, which we normally express as a scalar quantity, because you have a line vector here. It has to be now dotted with another vector, but it turns out you need a combination of the k, which is in the plane, cross product with the normal to the surface. Okay, so let's see if you remember your geometric interpretation of the cross product. K is in the plane of the surface and is perpendicular to it. What's the K cross n hat? The question is, does it lie in the plane or perpendicular to the plane? I should probably just say, is it parallel to the plane or it's perpendicular to the plane? Okay, so think about it. So the question is about K cross n, and the question I'm asking is it perpendicular to the surface or is it parallel to the surface? So send me a private message in the chat, A or B. Okay, I'm going to open up the chat. I can see it. Okay, all right. So I didn't get all the answers yet. I have some of them. 1, 2, 3, 4, 5, 6, 7. I have 7 answers. 8. 9. Okay, so let me now do a statistics on it. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So I have about 10 answers, and they are equally split among A and B. So it looks like you have to now go back and look at the geometric interpretation of the cross product. So that's going to be an exercise for you. Okay, I'm going to try something different. So I'm going to pick out on couple of you, one who has answer A and the other one who has answer B. And your job is to come online and verbally explain why you think that's the answer. Okay, so I'm not letting you off the hook completely. You now have to explain why you think the answer that you got is the correct answer. So the first person I'm going to pick out is let's see, I want somebody with an answer A and B. Okay, so I'm going to pick out Alex. and Arefur. So Alex, you go first, and you explain why your answer is what it was. You can unmute yourself. Yeah, go ahead.
Okay. Well, I actually wanted to change my answer.
Okay, very good. So that's good as well. Yeah, you can try. See, the process of trying to explain it, it sometimes helps. So change your answer and explain it. That will work as well.
All right. So K is in the plane, right?
Mhm.
And N is perpendicular to it. So the
Right.
cross product has to be perpendicular to both of those.
Both of them, right?
So in order for that to occur, it also has to be in the plane.
Okay. Anybody wants to add anything to that? Or anybody who is not agreeing with that, can you explain to us why? Anybody? Let me see. I would like to pick on somebody here. Moriam, you want to say why you were thinking the K cross N vector should be perpendicular to the plane?
No, I give A parallel, not perpendicular.
Oh, did I? No, your answer is B, which is perpendicular to the plane.
B, okay.
So you want to change your answer again as well?
I think maybe.
Okay. Okay, who wants to, who is still sticking to their answer that K cross N should be perpendicular to the plane? I want to hear your thought process, why you think it should be perpendicular to the plane.
Excuse me, doctor.
Yeah, go ahead, Khaled.
Well, I think we have to distinguish which plane we are talking about.
Mm-hmm.
It's the plane that contains K and N, right?
No, we're talking about the plane in which the K exists, right? So N is just the perpendicular to that plane. So the plane actually is defined already for you by the N vector. The normal vector to the plane defines the plane.
Yeah. So
what are the thoughts? Any ideas?
I think I need to show it on camera if you don't mind.
Okay, yeah, show it.
I don't know if you can see me now or not.
Yeah, we could see you. I could see you.
Yeah. So if we have this, like this is the K plane,
Mm-hmm.
right? And this is the N,
Mm-hmm.
right? So the cross product of them will be on this plane, like this. Or
so you're saying it's not going to be in the same plane as K is? Is that what your assessment is?
No, it's gonna be the same plane, but
okay.
it depends on the direction of K.
Okay, very good. Okay, that's good. So
Yeah.
you're now explaining a little bit in more details what Alex said. It has to lie in the same plane, but it also has to be perpendicular to K, right?
Yes.
Okay,
yes,
so let's.
I want to say.
Very good. Thank you very much. So what we're going to do now is think about this in simple terms, which is possible, right? So I will just draw maybe a couple of diagrams here, right? So for to define a plane, you need two vectors, right? Everybody agrees with that? Two perpendicular vectors. Or you need a normal vector at any given position. But the thing with normal vector is the normal vector is not constant, it depends on the shape of the plane. So if the shape of the plane is changing, then the normal vector itself is going to be different at different points in space. Actually, the same thing would work for these two perpendicular vectors. But let's assume we have a flat plane, like for example, the XY plane, right? So here's the Z-axis, X and Y, X, Y, and Z. And then the XY plane is governed by essentially the two unit vectors that are perpendicular to that plane, right? You know how we use the unit vectors to describe the geometry, right? For 3D, you need 3 unit vectors. For 2D, you need 2, and so on, right? So if you look at now a k vector, which may be in some random direction here, right? So I'm going to draw k like that. And then you have, let's say at this particular position, n vector is over here. So n and k form a plane as well, right? Now, if n and k form a plane, the k cross n is going to be perpendicular to both of them, right? And so it's going to be in such a direction, because it is going to be perpendicular to n, it has to lie in the same plane, right? So that this perpendicularity tells you that it has to lie in the same plane as k, and the fact that it also needs to be perpendicular to k tells you that it needs to be perpendicular in direction, or 90 degrees away from where the direction of k is. Does that sort of make sense? So k and k cross n will form a plane, n and k will form a plane, and n and k cross n will form a plane, and all of these 3 different planes have to be perpendicular to each other. And so with that, with those constraints, you actually have no other choice but to put this in the same plane as k.
Dr. Kapale,
Yes.
can you repeat it, please?
Yes. Right.
Thank you.
So think about this again as, first, the vector k is provided, right? So I'm going to just highlight it. Vector k is given to you at any given position. Let's say, you start from origin, and then the normal vector, because normal vector to that plane in which k lies is already given to you. So n and k are already given to be perpendicular to each other, because k lies in a plane, n is perpendicular to the plane. Make sense? Everybody with me? Now let's figure out k cross n. K cross n is going to be a vector, and we have to figure out its orientation, right? Now, how do we figure out that orientation? From the cross product definition, it's kn, the direction of the k cross n is always perpendicular to both the vectors. So if it is now, so I'm going to use one information at a time. Given that it's perpendicular to n, the only thing that's perpendicular to n is this plane in which the k lies. That means k cross n has to lie in the same plane as k. Does that make sense? So if n is perpendicular to k, n is also perpendicular to k cross n. That means k and k cross n, these are 2 vectors, will form a plane. It will be the same plane. Everybody with me? Fatima, does that help?
Yes, it's
Okay.
clear.
Okay, and then the second thing, right? So that's just the first condition. The second condition says that k cross n, it needs to be perpendicular to k. Okay. Vector as well. So it's like, let's say k gives you the x direction, n is the z direction, then k cross n would be along the y direction, right? So if you want to take a specific example of that. So remember, even though some of this stuff is repetition of what we have seen, some of these things are pretty basic in terms of what you have learned before in your earlier classes. Though given the answers, I thought I should explain. And so please don't forget your old stuff. There is now you should be looking at it in new light, and don't just take sides, choose answers. You want to have a logical explanation as to why you are choosing that answer. Okay, everybody with me so far? Let's now move on to one other very important assumption in electricity and magnetism is the conservation. Now, so far in all of your study of physics, if somebody gave you a conservation law, you have assumed that it's perfectly valid and always followed. Not quite true, okay? It's never the case because you have to quantify all of those laws. Remember, physics is an experimental science, and so everything has to have a quantification associated with it. There would be uncertainties, there would be errors in the results of the measurement. So you can make statements only up to a certain level of experimental accuracy. Okay, so that's going to be important. So even electron itself is not something that is permanently stable. It has a lifetime. And the lifetime of an electron is about 10 to the 24 years. This, of course, you need a little bit deeper knowledge of quantum electrodynamics and so-called particle physics to be able to figure this out, right? But that's the idea. That's what we know based on experimental data, that the lifetime of an electron is about 10 to the 24 years. Age of the universe, on the other hand, anybody remembers what's the age of the universe?
1.38 into 10 to the power 10.
Okay. So it's about, 10 billion years, right? Okay, so roughly about 13 billion years. We know that from our experience. So within the lifetime of universe, the electron is not going to decay. So then you can assume, okay, charges are going to be conserved because electrons, once you started with a certain number of electrons within the lifetime of universe, they're not going to go anywhere. They will be there, right? So that's conservation of charge. And all of our charges are for now, and we're worrying about only electrons, right? Same thing applies with protons, of course. And so then overall, conservation of charge makes sense, right? Then the other thing that's important is if now charges can move around in space, so you can associate certain amount of flux with that. And so let's take a certain volume with a certain boundary and a surface, boundary surface S. You can calculate the total amount of current that is flowing out of this volume. And so when the current flows out of the volume, the way you measure it is its flux along the boundaries. You look at, let's say you think about current as a vector and write down draw all of the little vectors, the vector field. Then if you look at this quantity at each point along the surface, that's going to give you the total current that's flowing out of that volume. And so that is also going to be equal to, using the divergence theorem. What should it equal to? Anybody? Divergence theorem. So what should I have in the volume integral?
Del dot J.
Right, it's the divergence of J within that volume. So volume integral of divergence of J, right? So you calculate the divergence at each point in space and add it all together for that given volume, and that's what gives you that, right? And so this is how you can figure this out, right? Now let's take a look at the total change, time rate of change of the charge, which will be lost as the current is flowing out of the volume. You're basically going to lose. If you look at the total volume of total charge in that volume, that's going to get we are going to lose the charge because the current is flowing out. And so that is going to be equal to the volume current density, time rate of change of that, right? And it's going to depend explicitly on, we can take that time derivative, put it inside the integral. It's okay to do if you are a physicist. For mathematicians, they would complain about it. We don't worry about it so much, right? So it's going to be partial derivative of rho with respect to t. Okay, And so then what we do now is compare these two. So let me use actually a different color here. These two volume integrals, compare them. And when you compare them, you're going to see that divergence of J and del rho of del T need to be related with each other. And so the way they relate with each other is partial derivative of rho with respect to T plus divergence of J. If you add it all together, it is going to be 0, right? Because the I is equal to dq over dt, overall sort of the average picture of things. On average, this relation should be valid. And so you're going to get divergence of J plus del rho over dt, which is the explicit time derivative if rho has the time dependence, which it would in this case when it's moving around. And this is called a continuity equation. Right. And so how is this related to law of conservation of charge? That means charges are not created, they are not getting destroyed. Anytime you have a current, which is a motion of charge, it's coming because you have time rate of change in the density. The density is going away from that volume of space. And so the only way you can explain the existence of currents is motion of charges, which is essentially time dependence of the charge density. Okay, everybody with me? So that's the continuity equation. It's extremely important. It is always followed within even a given volume. And in fact, this is actually related to every point in space. So it's valid at all points in space.
Excuse me, doctor. I have a question. Might
Sure.
be not so relevant or what we are saying, but if we are saying that the charge of the universe is constant, right?
Mm-hmm.
And also it always keeps moving from place to place. Let's say like that, right?
Mm-hmm.
So that means the charges and the electricity will remain forever, and the only energy we need it's in the making the potential difference between the places we want them to move from one place to another.
Mm-hmm. That's right. That's right. Yeah. So to create potential difference, you have to move those charges, right? So that's we will take a look at this in a little bit more details, at least in the context of electricity and magnetism. But you're thinking right. That's how it would work.
Thank you.
Okay. Now let's take a look at discrete charges moving. We were talking about continuous charge densities. And so you could think about rho of RT as some collection of charges like we saw R minus RK. That's how we write sorry, not infinity, it's finite number of charges at positions RK. And then let's say the velocity with which each one moves is VK, then you can write down the corresponding current charge, the current density as going to be K equal to 1 to N QK VK, and then the delta function R minus RK. Everybody with me so far? Okay, so we have basically defined two important quantities, which will then allow us to define the other important quantities of the electricity and magnetism. These are essentially the sources, the charges, and the charges and the current densities are the sources for electric and magnetic fields. So far, though, we haven't really talked about the field concept. You, of course, know from your undergraduate classes that you need fields. Fields are good, but why? Let's kind of take a look at them very carefully. So 18th century experimentalist, Priestley, Cavendish, and Coulomb all in Europe, right? At that time, the main activity in physics was happening in Europe, who figured out that the force between two charges, let's say we have a collection of discrete one of those are easy to understand to begin with. So you have one test charge and then another collection of charges which are labeled QK, then you get the force between them to be like this. Okay, so because you have a full r minus rk vector in the numerator, you have a cube in the denominator, but dimensionally it is 1 over r squared, right? So this is action at a distance. Now, you know, for gravity, we have similar situation, action at a distance. It bothered Newton, and we had to come, only when Einstein developed his theory of gravity, we understood what that action at a distance means. Now, you don't really need action at a distance if you introduce the concepts of field. And so the field concept for the first time came from Faraday. So if you think about gravity as a field also, then you don't have to worry about the action at a distance, right? For example, it takes the sun's light to propagate to us about 8 minutes, right? So what if the sun was to vanish suddenly? How long will it will take for Earth to figure out that the sun is no longer there, and then it has to change its trajectory, right? Because it doesn't have to follow it anymore. You can think of that if you think of the action at a distance. Even though they are at a distance, gravity, has certain magnitude because of the distance between them. There is apparently no connection between them, right? There is no talking between them going on, no communication between them going on. So how does this action at a distance happen? It's perplexing. It's complex. It's not very easy to understand. It's kind of counterintuitive, and so it's not. And of course, that cannot be how things can happen, because you can't instantaneously pass information from one point in space to the other point in space. It depends on how far they are, and that's going to determine how long it takes. And so action at a distance is an odd thing, right? So this is odd. It does not make sense, even though Newton told us that. Same thing appears here in electrostatics. But what Faraday did was he said, you don't have to worry about this action at a distance. The field is there everywhere. The moment you have a charge sitting at certain position in space, it creates a field. So it modifies the environment. And once the environment is modified, a motion of that charge will be propagated through this field, and then that will be communicated to the other charged particle at a certain different position in space, and it's going to know. So there is no action at a distance. There is now communication at the speed of light. Okay, everybody with me so far? So Faraday said, just even though experimentally force is the quantity that you measure, it is the concept of field that allows us to make sense of the values. And so this is important because only local values matter. You don't have to travel anywhere. So for example, for Earth doesn't care whether the sun is there or not. What it cares is what's the gravitational field at that location, and then it just responds to it. And Einstein, of course, took this idea even further. He says the space itself is deformed, and so Earth doesn't even have to worry about this gravitational field, so to speak. It just is moving in a deformed space, and so it has to just follow that. And so the same idea kind of works even here. You can think of these electric field as some mechanical deformations within the volume of space that to which the charges are responding to. And that is actually some of the initial thinking historically was about electrodynamics. Maxwell, for example, was very big on mechanical models. At that time when Maxwell was working on these, mechanics was the most successful theory of physics at that time. And so everything somehow had to relate to mechanics for the scientists at the time. And so for most of the concepts that we will see later on, Maxwell had mechanical models for them. One of his important contributions, which we will learn about later, the displacement current, he also had a mechanical model for it. So that's how all of that process sort of works. So if we have the field, now we should be, we're going to stick with, let's say, electric field as a quantity that permeates the whole space. Provided you have certain charge, you should be able to write it down, right? So let's take the, let's devise our coordinate system first. So here's our coordinate system. We have some charge distribution, rho of r prime. And to be able to distinguish the source positions, which are r prime, from the point at which we are trying to find the electric field, let's call the sources as r prime always, and the observation points as r always. Okay, so that's going to be our notational choices here. And so we do this. Okay, and so this is r prime, that's r vector. And so what matters really is the distance between the source point and the observation point. So this is r minus r prime vector. Okay, so now the source charges, the rho r, they are distributed in space, and ER is a specific point. So that's why the integral here is over the coordinate r prime. You have to sum over all possible r primes, and then the summation in continuous domain becomes a integral, as you all know, and you would have then r minus r prime, which is the distance cubed. Okay, so that's how you get the electric field. All that has happened now is the Q is gone, and we replace the QKs with the continuous volume charge. Okay, and what this essentially also tells you that you have superposition principle. That means if we start building your charge distribution one charge at a time, you bring in the first charge, you get certain electric field, you bring in the second charge, the electric field that you get would be the electric field of the first charge when the second one was not there, plus the electric field of the second charge when the first one was not there. You just kind of add them, and that is the superposition principle. So superposition concept is not just completely quantum. It is this is something that we talk about all the time when we're thinking about quantum concepts, but it is a property, linearity property of even electric and magnetic fields. You just add things together. It's same thing applies for gravitational principles. So the magnetic, the gravitational field at the position of Earth is not just because of the gravity of the sun, it's also the moon, also the other planets. But of course, it depends on which one has the prominent magnitude, and sun happens to be the most influential when it's the absolute value of the gravitational field that you need. When you start talking about tides, which are gravitational field difference along the diameter of the Earth. So the gravitational field at the point that's near to the sun is going to be even larger than the gravitational field at a point that's farther away from the sun on the Earth's surface. And so that difference, it turns out, is actually larger for the gravity of the moon than for the gravity of the sun. And so you get these tidal effects coming because of that. And so there are interesting scenarios there. We don't talk about the tidal effects in electrostatics at all. It's only in the domain of gravity because the objects have much larger sizes. So size effects are important in gravity, not so much in electrostatic, except for the difference between the macroscopic and microscopic domains, right? But the macroscopic in E&M is also of the size of several millimeters, not like hundreds of millions of kilometers like in gravity. Okay, so for your second homework, you did several manipulations of the gradient operator operating on different scalar and vector fields. So I'm just going to recall some of the derivations that you did here, and based on those, you can actually derive a couple of Maxwell's equations also. So everything starts experimentally. Remember, this is an experimental finding. Faraday, like I told you earlier, at that time, theory and experiments were not done by separate people. You would basically do both. And so Faraday brought in this concept of field, which just made calculations a whole lot easier. Also, it allows us to get away from this odd concept of action at a distance. Nevertheless, to develop the theory further, these differential operators were studied by Maxwell. And of course, remember, he did not have, I don't know if you know this, he did not have access to these operators. They were not defined. That notation was not even invented then. In fact, the vector notation itself was not invented then. So imagine the kind of plight that you would have to go through to summarize all of these equations. So, this divergence equation is actually very, very easy to write down, even in the fully scalar notation, but not the curl equation. And so curl equation would amount basically to 3 more equations. So the 2 of the electrostatics Maxwell's equations that we write down simply now in the modern times, Maxwell had to write down 4 different equations to be able to deal with that. So he had, essentially overall 8 equations that he had to carry and make sense of and put them together. So combining these two, we can show, and I think it is, if it was not there in your second homework, it will be part of your next time homework to actually prove this, right? To prove the first 2 Maxwell's equations, which is divergence of E. Okay, how do you do that? The experimental, right? This is also experimental reality because you measure experimentally the forces, and then you took one level of sort of higher level sophistication, which is brought in the concept of electric field, but this is still experimental. And so then by understanding the properties of these del operators applied to 1 over r minus r prime, you can then show that divergence of E is going to be epsilon 0. You may have to use the divergence theorem and the Stokes theorem, but the idea is to rigorously go through the mathematics and prove that. And that's something you can do since you're all grad students and you have seen some of the math before. It's going to be something you will be doing in your homework. We are not going to be doing here in the class. Any thoughts, any questions so far at this time? Okay. All right, so we're going to now look at magnetostatics. Again, a very, very cursory overview like we have been doing. Okay, and this one also started around 1600. Actually, magnetostatic ideas are older than the electrostatic ideas. People were fond, they came across these magnets, which are naturally occurring materials. And then they saw that it has interesting properties and they get applied. Even in everyday life, it's difficult to understand magnetism in its details because you have to actually, to truly understand it, you need to bring in quantum effects. It is a quantum phenomena. Magnetism could not have been there without quantum mechanics, strictly speaking. But it survives in the bulk materials, and it's very easy to use. So you see, refrigerator magnets and such. So very commonly used. Electrostatic phenomena on the other hand, you won't find it very commonly in everyday occurrence. Nowadays, of course, if you look at modern equipments like the printers and copiers, they use electrostatic phenomena to allow the ink to stick to the paper. So that is happening electrostatically. They use electrostatic forces to be able to do that. And so there is a certain mechanism inside a printer which allows you to do that. If you, as a part of this class in the past, I haven't done this in the last 2 or 3 times I taught it, but historically we always had sort of a literature survey type project in the class. You guys let me know if you would like to do a project, and that will take away one of your exams. I cannot take away the final exam because you have to have certain elements of assessment that we have to report on, but we can get rid of one of the tests if you like, or we can reduce the weightage of the final exam, just to test you on the core concepts, and have the project as the important component of your grading for the final. So let me know if you would like to do that. And now is the time to answer. You could just let me know in the chat, project or no project. Okay, just send me a private message so that you don't influence each other, and I will make a note of that later. Okay, so this is about, I will continue the discussion and I'll monitor the chat in a little bit. So in about 1600s, we understood that natural magnetism is naturally occurring magnets. Even the name magnet comes from a place in central Greece called Magnesia. And the material was lodestone. So these are naturally occurring, material that were mined, and they found them to have magnetic properties. Then for quite some time, nothing happened. Almost 200 years, nothing happened. And then 1820 came Ørsted. He's a British physicist, and he showed that sort of the connection between electricity and magnetism, that the current carrying wire can generate magnetic field. So again, that's an experimental connection that we came across, that those two things relate. Another important person, French physicist Ampere, who figured out that if you have two current carrying wires, there is a force of attraction or repulsion between them, sort of like the Coulomb force, right? And so he found that if you have two current carrying wires, and let's just take two loops here, one loop here, another loop there. Let's say the current is flowing in this direction in the first loop, and sorry. And then let's take another. So this is let's actually label them to be a test loop. So this is just like in the case of the Coulomb forces, we took a test charge in the presence of a discrete set of charges, and then we figured out how it's going to, how they are going to respond to each other to find the total force. Here we are going to do the similar kind of thing. Let me actually change the color to black for the coordinate system. Okay, so we have this coordinate here, that coordinate there. And I'm going to call this RK prime. That's our source. And let's say it's labeled with a K. You have many more of those, right? You have a collection of those. And then you have the coordinate R of the position at which we are trying to find the magnetic field, or rather the force. Rather, again, you have to measure the force, right? That's the idea. And this is the small line element of the current carrying wire that you are going over, right? So let's calculate the force. The force, of course, they measured it experimentally and then theorized that it would look like this based on the values of the coefficients and the other processes. So you need, of course, the integral over the first loop, a control loop, because it's a closed loop. So all of the forces acting on different points of the loop will have to be added together. That's why you have this. But the force arises from each one of the source current loops. So you will have k equal to 1 to n. Let's say you have n of these loops. I'm going to move this down here so I have some more room to write. And then you have the integral. Now you need the loop over each current loop. So ik dot dlk has to be determined at each point, and then you you do the contour integral for that, which is just basically a closed loop integral. It's not very complicated because there is nothing that is flowing up, so you don't really need complex integrations. But each one of those current loops are going to contribute through the same kind of quantity that we observed in the electrostatic case, this distance, the geometric parameter, r minus rk over r minus rk cubed. Okay, everybody with me? So that is the Ampere's contribution, or what we call Ampere's law. Okay, now, just like Faraday, again, this one is also Faraday. Faraday, of course, also studied magnetism and the connection between electricity and magnetism. So he introduced another field concept, right? He said, okay, magnetic field, maybe there is a field, just like in the electrostatic case. And so he started saying, okay, let's get rid of the test loop out. So without the test loop, can I write the rest of the stuff as a quantity that then only locally matters? So you get I dlk, ik dlk, that part stays as it is, and then the distance parameters over r minus rk magnitude cubed. Okay. So what then matters is you have the magnetic field defined in space, right? So certain vectors. I'm not very careful in designing this, but then you have this current carrying loop that's situated there, and then that current carrying loop is going to have a force it's going to experience because of the magnetic field, and that force then can be written down as I dl crossed with b. And we already know this has, because of the cross product here and b itself being a axial vector, f would be a normal vector as you would expect, right? So this is the magnetic force in the expressed through the field concept. Okay, everybody with me so far? Now here we had discrete currents, right? So this is a discrete representation. Discrete current loops giving you the magnetic field. We can write similar expression if we had a continuous current density through a given region of space crossed with, again, you can see cross product is very, very important, always occurs in magnetic field expressions. You need to be very careful. Okay, and that's what is going to give us the magnetic field due to a region of space like this, for example, not a surface, actually, say a volume current. And you have current density J of R prime going through it. And let's bring in our coordinate system again. I want to try to find the magnetic field at this point in space. This is our origin, and that's our sources. This is R prime, that's R, And so what matters again is the r minus r prime, and we are trying to find the magnetic field at this point in space due to some source that we got. So that's why the integral is over always r prime. Okay, and so with this, again, using the properties of the del operators that we saw earlier, this leads to the other two Maxwell's equations, which is divergence of B equal to 0. And you're going to be able to prove that, and curl of B is equal to mu 0 J, the current density. And here, of course, we're assuming that divergence of J is equal to 0. This is the electrostatic condition, right? Because in electrostatics, we assume that there is no explicit time dependence on the charge density. So partial derivative of rho with respect to T in the continuity equation is 0. And so this is also going to lead to divergence of J equal to 0. These are these electrostatic conditions. So imposing electrostatics gives you divergence of J equal to 0 always, right? So that's the other connection. Now, because electricity and magnetism are connected right now, the two equations, the four equations that we have seen so far, the divergence and curl of the electric and magnetic field, they don't seem to be connected with each other, except for a slight connection here in terms of the current density J, right, which is related to the charges, but you don't quite see the dependence of any of the derivatives of B on E or derivatives of E depending on B. You don't quite see that yet. For that, you need Faraday. Faraday's law is bringing in that connection. And so Faraday's law says negative time derivative of the flux of B through certain surface, right? So if you look at the magnetic field that's passing through a surface, if that flux is changing, that is going to introduce currents in that loop, right? And R is just the resistance of that loop. Okay, and all of these things were initially done experimentally, of course, right? And then the negative sign comes from Lenz's law, right? So I can kind of give you a couple of situations here. Let's take a loop of current. And let's bring a magnet. Draw a magnet with a and let's bring the magnet in such a way that sorry, the north pole is facing the loop and south pole is away. And so in both cases that we are going to study, we do exactly the same thing. However, in one case, we bring them closer to each other. So the magnet is approaching with certain speed to the loop. And in the other case, the magnet is going away from the loop. In that direction. In this case, now what you want to do is the flux is calculated in the plane of the loop. So I'm going to actually now show the plane. So the plane of the loop matters, not just the boundary. Okay, and in one case, let's say in this case, as the magnet comes closer, the flux is increasing, the magnetic field is pointed inside and into the plane of the board, and ds dot b, because the magnetic field is going to change direction slowly, and it's going to go up almost in the direction of the normal to that surface as you bring the magnet closer together. And so ds dot b, the quantity, the flux is going to increase with time. If it's going to increase with time, then the current that you get has to create a magnetic field. Okay, so magnetic field is increasing, it's in that direction. What should be the direction of the current? I will give you two choices. Choice A is counterclockwise, and choice B is clockwise as you are looking at the loop. So even though we're looking at the loop from sideways, think about it as if you're looking at it from top down. Which way would the current flow using that negative sign? And you know the Ampere's law, right? You know the direction of the magnetic field. You have to use the right hand. If you are curling your fingers in the direction of the along the loop in the direction of the current, then the magnetic field is given by the thumb, stretched out thumb. And the Lenz's law said the induced magnetic field needs to be opposite to the direction of the flux, the direction of the increasing flux. So what would be the direction of the current in these two? Let's give me the answer only for the first one, right? I only need answer for the first. Second one is trivial. Okay, so think about it. Yeah, I got a couple of answers, so start thinking. Okay, so from the rough analysis of the answers that I got so far, again, they're equally divided, roughly speaking. So that means you guys need to review some of your undergraduate material. You don't seem to remember some of it. And so it's important that you do this, right? So I'm going to just directly give you the answer. Now the answer is A here. Why? Because the flux is increasing in the downward direction. You want to oppose it. And so the magnetic field created by the current loop needs to be going up. And so for that, you need a counterclockwise current. And so it's the A direction that's going to be important. Or this direction, that's where the direction of the current will have to be, so that it opposes the change that's occurring, right? Always remember, don't forget Lenz's law. And in the other situation, now the flux is decreasing in the upward direction. And so you want to increase that flux. And so the current has to be now in the opposite direction. Okay, so just to point out the notation here, diagrammatically for you to take a look at contour C and the surface S. And you can think of this as, so let's take a look at it specifically. I and R that we had in the previous relation, I'm going to explicitly write that down in electrostatic terms. It is essentially the line integral of the electric field along the direction of the loop. R is the resistance. And E is the induced EMF. Okay, so then we can relate this time derivative of the magnetic flux, ds dot b, is going to be equal to the contour integral. So that's where the S and C are coming from. Contour integral of E along that contour, and we can use the divergence, the Stokes theorem to simplify the right hand side, which now becomes a surface integral also. So ds dotted with curl of E. Okay, and so then the curl of E, because both the sides now have a surface integral, you can get the integrands to equal to each other. So you get curl of E equal to negative del B over del T. So it's in the The negative sign is important, but now this allows us to modify the Maxwell's equations that we saw, and this is due to Faraday, right? Because this is Faraday's law of induction. So this is the first modification to Maxwell's equations that was suggested. Again, we are looking at sort of the history, if you will, of how these things came about. So we started with, let's quickly review what we did. We started with the electrostatic Coulomb's law, experimental. From that, the field was introduced, and then by looking at the geometric properties of the gradient operators, we got these two Maxwell's relations or Maxwell's equations. Maxwell's relation is a wrong term here that is used in thermodynamics. So we will talk about that later when we do statistical mechanics. Some of you have already seen that. So divergence of E is rho over epsilon 0. The curl of E is 0. Okay, that's what this says. But the modification tells you that if there is magnetic field around and if it is time dependent, then curl of E is not 0. You get the curl of E to be non-zero. So that's why it's a modification to the most basic forms of the laws. Divergence of B is 0. That means there are no sources. So you don't have individual magnetic poles, but you have curl of B, which is mu0J. So the sources in this case are complicated. They give you curl rather than the divergence. And those two also will have to be, one of those will have to be modified. That's the contribution from Maxwell, but we will take a little divergence here. We will not look at it today. We will look at Maxwell's contribution, which is the displacement current, in the next class. What I want to do in the remaining 3 or 4 minutes is take a look at the examples. Remember, I promised you I will give you examples of using the delta function for describing charge distributions like we did for the discrete. Let's now take a look at a spherical charge distribution. Okay, just as a quick example. So delta function examples. And I want to look at a spherical shell of radius r and charge on charge density sigma, surface charge density sigma on the, so we don't need to say anything beyond that. That's good enough. So how do we write down this as a volume charge density? The goal for delta function is, doesn't matter how your charge is distributed, whether it's 2-dimensional, 1-dimensional, or discrete charges or anything, you want to be able to express it as a volume charge density, right? So the goal always is express as a volume charge density. So this rho of r would have some dependence on sigma, right? But we don't know what that is, right? So that is something. Or we can even just say total charge. Total charge Q. So you can then relate Q and sigma. And so, but this has to be written down now as a delta function. So it is going to be, you can sort of see the volume charge density is not spread everywhere. There is no inside the spherical shell, there is no charge, only on the surface. That means you have to pick specific value of the radial coordinate. Theta and phi don't matter. And so it is going to be some constant. So this is a constant proportional to the proportionality constant, which is going to be delta of r minus r. Everybody agrees? There are no other restrictions. That tells you that whatever that charge density is, it's going to be delta r minus r. Now, how do you make sure that this is correct, right? Because it's now a delta function, it's very easy to see. You need to do a volume integral d cube r of rho of r. and that should be always equal to the total charge Q that they gave you, which you can write that as sigma over 4/3 pi r squared, right? That's the surface area of the sphere, or is it's just 4 pi r squared, right? Sigma over 4 pi r squared, that's the surface area. And then you, yeah, the ratio gives you Q. And so you just have to do integral C delta of r minus r d cube r. And because it's a delta function on the right hand side, you can write down d cube r as r squared sine theta, d theta, d phi, dr. And so you can actually do the volume integral in the 3D spherical using the 3D spherical coordinates. And then that allows you to determine C. So try this at home, try to calculate C. And once you have the C, then your job is done. You have expressed this two-dimensional surface charge density is as a volume charge density with the help of delta functions. So that's the power of these delta functions. It just makes the application of Maxwell's laws extremely easy if your charge density is expressed as a volume charge density as opposed to surface charge density. And so things become easier, but you need to be able to manipulate delta functions to be able to figure that out. And that's the process. So that's it for now. I went over a couple of minutes, but I wanted to give you a flavor of this. There will be a couple of examples in your homework problem so that you get some practice playing with these delta function ideas.